So, let's take a look at now question number 8. You probably noticed that the count of each bean species were not equal in your tree grid cells. Do you think the variation is significant, or is it because of the sampling error? Well, let's first take a look at those numbers, right? Over here. Um, well, yeah, first two is more or less the similar, same, but the last one is a little bit higher. So what I have done over here is actually, in order to do the next step in statistics, I created this particular table, and in 1 to 3 cells, I have mentioned what my sampling size is, right? You know what I gotten. So yeah, so you do see they are not actually the same, right? So there are differences. Now, what could have resulted in this difference is what you need to answer for that question. Question number, I think it's 8. Yeah, it's number 8, right? So is it sampling error? Yeah, sampling error could have happened. Could there be anything else happening? Yeah. So if this data collection were done by multiple people, there is an observer bias, right? In terms of doing the sampling, with that spoon kind of scooping things up, there will be slight differences between different observers or different surveyors. So that's actually one source of error, right? Some sort of an experimental error in that case. And then if you look at the actual sampling design we used, right, in this grid table, right? So what if there were some beans lying on right on top of these grid cells? Um, well, we did not specify a particular rule whether to count them in or discount them, right? So if different observers actually use different rules to count or discount them, that could have also added an additional design error, right? So that could also lead into um, unequal or uneven numbers of each particular species, right? So there are many sources of errors: experimental, observational, um, and design errors, right, that would have occurred. Could it have been also the sampling error? Yeah, it is possible, like sampling just 25% of the entire population could have resulted in some sampling error. Other non-sampling error situations are also there. These beans are quite very, similar to each other, so those species are not that different, easy to identify separately. So that could also create some sort of an observer bias. So answering question number 8, yes, some of them could be related to the sampling error, inadequate sampling, um, or inadequate sampling, number of times being sampled, could have resulted in this error. But also know that there are some other non sampling error, like observer biases, experimental errors, design errors happening, right? So remember, guys, like when you answer these questions, please do spend some time explaining these answers. Don't just rush through them. Don't provide half-hearted answers. I don't like it. Okay. Now, in order to answer this question, right, the question is, in your worksheet, you have to test a particular null hypothesis. The null hypothesis is that the lentils species are uniformly distributed, and you're arguing it's not, because apparently if you look at your data set, right, I don't think it's uniformly distributed. And I also mentioned earlier that biological species are rarely uniformly distributed. They either have a aggregated distribution, right, or a random distribution. Like uniform distribution is very unlikely. So hence uniform distribution is what null hypothesis dictates. So that's what we are going to test using a chi-squared goodness of fit test. Chi-squared goodness of fit test compares two different types of distributions. One is what you observed, right, in your survey data, in your 15 bean communities, right? And this data set 47, 44, 55 is actually coming out of the actual observed data. Now, how do you calculate the expected data? Expected data is actually follows what? Uniform distribution, meaning you will expect equal number in cell 1, cell 2, cell 3, right? So how do we calculate that? In order to calculate that, we need to do something like this, right? Equals sum, right? Summation of these three numbers, right? And divided by the sample size. That is actually 3, right? Divided by the sample number, right? That is 3, right? and let's see how much that is. That's going to be about that 48.66. So on average, if lentils were uniformly distributed throughout this 12 grid area, right, I would expect the equal numbers in each cell, right? So I'm going to round this up, 48.6 as 49, and I will put 49 in all of these three, right? So the same case in your data set, right? Average these three up and copy that number as expected. Now let's try to do this very little calculation, right? So what we are doing over here is we are calculating the difference between observed and expected. And then remember, when you calculate that, right, some of those numbers will be negative, right? In this case, 44 minus 49, that's negative. 47 minus 49, negative, right? So in order to get rid of the negative sign, we actually raise that difference to the power of 2, right? And then we divide that by the number expected. So this is very simple formula, and let's see how to type it. Equals, right, observed, that is this particular reference, minus expected, right? And just following the exact format, I'm going to put parentheses around observed minus expected, and then I have to raise it to the power of 2. So in your keyboard, simultaneously press Shift and 6 to get that particular little weird symbol, and then type 2. And then what? Then this entire thing, right, divided by expected, right? Right, and then I hit this little check mark. That is actually my calculation for that particular value, right? And then what I need to do is I have to update that, for these three the other two cells, right? I need to calculate that particular value for all of them, right? Now for that, you can actually drag and drop. And now the last thing to do is actually calculate this particular value, chi-square, right? And then what? Then you need to sum all of these three up, right, over here. Like, again, what you do, put your cell over there, right? Go to the formula bar, equals sum, right? And give it this particular range. And close the parentheses, hit the checkbox, right? That is your chi-square value. Now it asks for degrees of freedom. DF stands for degrees of freedom. Degrees of freedom is sample size minus 1. How much is what is your sample size? Your sample size is 3. You sampled that bean population 3 times. So 3 minus 1 is 2. Right? Now what do? Well, you have the calculated chi-square value, you have the degrees of freedom. Now, in order to compare, now what you have to do is you have to compare that particular calculated value with a standard chi-square value. Now, for this particular case, you have to go to, in your lab manual, page 97. Page 97 actually lists for different levels of degrees of freedoms, right? A tabulated theoretical chi-square value. Now, what is the theoretical chi-square value that corresponds to your degrees of freedom? Your degrees of freedom is 2. That is 5.991, right? 5.991. Now, for all of us, the sample size is 3. So your theoretical chi-square is going to be 5.991, right? So what you're going to do now is compare that particular tabulated theoretical chi-square value with this calculated chi-square value, right? Now, in general, when you actually when you try to learn more about chi-square tests, which I actually strongly encourage you to do, please read in your lab manual pages from 93 to 98, right? Because that is actually going to be extremely useful to know what chi-square test is and what chi-square test does, right? I actually explained it briefly with respect to this Excel sheet, but you must read from page 93 to 98 to understand a little bit more about the chi-square value. Now back to what we have been doing, right? So Compare these two numbers, calculated and tabulated. Now, which one is greater, right? Is your calculated chi-square greater than your tabulated chi-square? Or is your tabulated chi-square smaller than is your calculated chi-square smaller than tabulated chi-square? Well, seems like the tabulated chi-square is greater than the calculated chi-square, right? So in that case, right, you fail to reject the null hypothesis. Let me repeat. If the calculated chi-square is greater than tabulated chi-square, you reject your null hypothesis. But if your calculated chi-square is smaller than tabulated chi-square, you fail to reject your null hypothesis. What was your null hypothesis? Let's go back to your data sheet and see for ourselves. Well, it wanted you to test the null hypothesis is actually that your lentil species are uniformly distributed. Okay, well, and you fail to reject that null hypothesis. So your inference is actually that the lentils are uniformly distributed, at least according to the data set that I used here. Okay, now what do you do over here? How do you answer these questions, right? Look at this question. Let's follow up this question. If null hypothesis is true, meaning if lentils are uniformly distributed, how many green lentils should you expect to find in each cell? We did the calculations already. Remember over here, 49 in my case, right? This total number divided by the sample size. Conduct your chi-square test. Construct a table in Excel showing the formula in your lab manual, right? And insert the table here. Well, I already have created one over here, so I'm going to actually copy it, right? And even format it beforehand like this, putting all the borders, making it pretty. Copy it, come back here, right, and paste it. Voila, right? Again, it's a table. I think this is my second table, so I'm going to give it a meaningful caption, right? I can say over here, can type chi-square test statistics, right? To test for testing the null hypothesis, blah blah blah, like that. Make a meaningful caption, right? And then that's it for that 10A. 10B, what are the degrees of freedom? Well, we calculated degrees of freedom, right? It is sample size minus 1, right? So that was 2. I think that's going to be 2 for all of us. Critical chi-square. Critical chi-square is same as the tabulated chi-square that I just mentioned. And people use different terms. Theoretical chi-square, tabulated chi-square, because it is reading out of a table, to a corresponding degrees of freedom, or critical chi-square, right? All of those three means same thing, right? And in our case, that was what? 5.991, right? And then degrees of freedom was 2. Draw a conclusion about the null hypothesis. Does the evidence indicate that green lentils are uniformly distributed among grid cells? Well, according to me, my critical chi-square was greater than my calculated chi-square. So no, I fail to reject. I cannot reject the null hypothesis. So I have to accept the fact that lentil species are uniformly distributed in the beans community. Okay, that's what it is, right? And you can explain how you came to the conclusion. You have to say that your critical chi-square or your tabulated chi-square or your theoretical chi-square was greater than the calculated chi-square. As such, I failed to reject the null hypothesis, right? As such, the distribution is uniform, right? Again, please read the textbook chapter on statistics to understand more about this particular component. Let's move on. 11. Briefly describe a realistic natural biological situation in which you would expect a species to be uniformly distributed across a landscape. I mentioned that it's hard to come up with an example where species are uniformly distributed. Mostly it's not. So I have several examples for non-uniformity. Think about any species that is territorial, right? Cliff nesting birds, right? For example, seagulls, swallows, right? Any cliff nesting bird, any group nesting bird, any colonial species are actually non-uniform in distribution, right? And I earlier mentioned some species tend to be clustered, some of them tend to be randomly distributed. So um, any distribution of mm, what else am I thinking? Elephants in a savanna, right, is going to be non-uniform, right? I mean, if they're uniform, that would be great. They're not, right? Distribution of any predators are going to concentrate on areas where there are prey. So any prey species, predator species can be a good example, right? Um, Distribution of amphibians, right, are going to concentrate on moist, wet soil, right? So they are clumped or aggregated, not uniform. Um, Pollinators, right, or nectivorous species are going to concentrate on areas where there are rich supply of nectar. So that's another example for non-uniform distribution, right? So I am going to challenge you to find yourself some examples for uniform distribution, right? So generally, if a particular species actually have the same competitive advantage, if they have equal competitive capacity, you might actually experience some example for uniform distribution, right? Or if species are territorial, but they are equal to each other in terms of their dominance, you might get uniform distribution, right? Certain forest birds that are songbirds could have this kind of a distribution, right? In forests that actually have even aged trees could have that uniform distribution. So that's enough examples, right? I'm going to challenge you and want you to find out some examples for uniform distribution. In your own words, summarize 3 important things you should have learned about sampling. Well, I've taught a lot today, right? So you tell me about what you learned about sampling, what you learned about statistics, what you learn about populations, right? Anything, right? It shouldn't be nothing, right? It should be something correct. I want to say 3 distinct things, right? What do you learn about sampling error? What did you learn about how to avoid it? Right? Why statistical testing are important, right? Why average, mean values themselves are less reliable, right? So anything that you learned today, right? I want to hear. Okay, that's it. You have a week to complete this assignment. Submit it through Blackboard. Good luck. I'll see you again. I see you back in a week. Bye bye. Good one.